Hello everyone. I'm Damian Ruiz and I'm going to discuss my thesis work titled Physical Properties of the Multiferroic System based in lanthanum-doped bismuth ferrite and strontium-doped calcium titanate. The bismuth ferrite, also known as BFO, is a material with a perovskite-like structure. BFO exhibits multiferroic properties, so it is considered a good prospect for device applications. Multiferroic materials exhibit simultaneously ferroelectric and ferromagnetic orders, that is, they are capable of being polarized by an external magnetic field or vice versa. As described in Figure 1, the ferroelectric dipoles in ferromagnetic domains are aligned in the same direction as the electric and magnetic fields, respectively. Furthermore, the synthesis of BFO has some issues as the difficulty of obtaining a single phase and the high leakage current. These problems can be resolved by substituting A and B sites on the BFO structure. There are some studies indicating that BFO doped with lanthanum and strontium can stabilize the phase of BFO, reduce leakage current, and improve multiferroic properties. The experimental part is shown in the following diagram. The samples were synthesized by the solid-state reaction technique. Also is shown the denomination corresponding with the X's values. The reagents in powder form were weighed on an analytical balance at the appropriate molar ratios and mixed in an agate mortar to homogenize. Subsequently, calcination and sintering heat treatments were applied at 830 degrees Celsius and 930 degrees Celsius, respectively. Once the powders were recovered, they were analyzed by X-ray diffraction and diffuse reflectance. The leftover powder was used to make 6 mm diameter pellets with a hydraulic press with a load of 0.5 tons, which were sintered at 930 degrees Celsius. The pellets were prepared by silver plating and cured at 300 degrees Celsius for 1 hour. Finally, dielectric and ferroelectric properties were measured by impedance analysis and PE hysteresis cycle tracer. Next, it is time to discuss the results section. Figure 2 is shown the X-ray diffraction patterns for the synthesized materials compared with the simulated BFO diffractogram, where the similarity can be observed. The profiles detected at values close to 32 degrees show the formation of two peaks corresponding to the 104 and 110 planes at lanthanum 0, as characteristic of the R3C space group. The peaks merge as the value of X increases, indicating a mixture of rhombohedral phases with another else. Figure 3 shows the SEM images of the fracture sections of the pellets, which have been seen in all specimens exhibiting irregular shapes. However, improvement in densification can be observed as the value of X increases. Figure 4 shows the relative permittivity and dielectric loss profiles concerning temperature for samples lanthanum 0 and lanthanum 15. As the value of X increased, a peak formed between temperatures of 230 degrees Celsius and 250 degrees Celsius, which decreased in size at higher frequencies. This behavior is typical of dielectric relaxation. Ferroelectric loops for the samples can be seen in Figure 5, exhibiting an improvement in ferroelectric properties. However, the rounded shape indicates some lousy behavior. The band gap values were estimated using the Q-Belka-Munk function, calculated with the diffuse reflection data, and the corresponding Tog plots were produced. Finally, extrapolating the linear segment in the Tog plot, the band gap values were approximated in a range from 2.21 eV to 2.13 eV, presenting a decrease as X increases. In conclusion, the synthesized materials exhibit a structure like that of BFO with X equals 0.0. But with higher values, it seems the formation of a mixture between rhombohedral phases with another phase. Furthermore, the dielectric and ferroelectric measurements indicate some improvement as the value of X increases, but with lousy behavior.